Bismillahirrahmanirrahim. My name is Imad Ali and the topic of my presentation is hybrid low radix encoding based approximate booth multipliers. It's just a simple booth, it has nothing to do with the project. So sequence. The sequence of my presentation is as slash. First, we will discuss the introduction of the topic, and then the two different approaches to booth multipliers are discussed. Then a slide presents the summary of what work has been mentioned in the paper. Afterward, we discuss two kinds of booth encoders, that is radix 4 and radix 8. Then we move on to the approximate booth multipliers. Afterwards, we evaluate the designs mentioned in the paper and compare them to the exact multipliers. Towards the end, we draw a conclusion of the work done, and then we relate to what we have studied in the semester so far. Introduction. Booth application program is a multiplication algorithm that multiplies two signed binary numbers in 2's complement notation. So basically it's just a multiplication technique that is used, and in this we don't have to actually use the multipliers, we can simply use the adders in the hardware as Dr. Rehan described it in the class. Afterwards, the radix. Radix is a term used to describe the number of digits utilized in a positional number system before what we can say rolling over to the next digits place. For example, in the base of 10 numbers, there is a total of 10 digits that are used from 0 to 9. So the radix is 10. Similarly, in the binary number system, that is 0, 1, the radix is 2. We also studied a radix 4 system that consisted of numbers 0, 1, 2, 3, and so that's what radix is. So why do we need the approximate computing? A large number of applications today actually require customized hardware with low power consumptions. Conversely, the amount of data which needs to be processed by these hardware modules has increased drastically. Therefore, it becomes difficult to meet both the opposing requirements. So, approximate computing has emerged as an alternate to meet the above mentioned challenge. Approximate circuits generally refer to the approximate design of the arithmetic unit, such as adders and multipliers. For quite a long time now, the fixed bit booth multiplier has been studied. We also studied it in our class, and it uses truncation based approach. Now basically truncation achieves the hardware gain which we are looking for, but it also incurs a large amount of error. A paper presented by Wei Sheng and T Chang uses a probabilistic estimation to drive an error composition formula for a fixed width booth multiplier. So a broken booth multiplier is designed by removing the carry save adder after the specified vertical break length. Now the second approach for design approximate booth multipliers as persuaded in the technical literature is using an approximate booth encoder. A paper presented by H. Yang and T. Cheng and J. Han proposed an approximate recoding adder that reduced the long carry propagation for radix 8 booth multiplier. The design of approximate radix 8 booth multiplier generates a small number of partial products and thus requires fewer adders to accumulate partial products as compared to that of radix 4. This is because generation of plus minus 3x multiplicand in a radix 8 encoder requires a preliminary processing. Therefore, a higher delay of 10 to 20% is observed than radix 8 algorithm. So what's the solution for this problem? So a solution is that we round it off to the nearest power of 2 by shifting. So moreover, the said approximation is handled such that errors complement each other in contrast to high radix approximation. Additionally, the concept of hybrid lower radix encoding is introduced to explore the accuracy energy trade-off for approximate booth multipliers. In this slide, we discuss what the contents of the under consideration paper. So the first section is just an introduction which we have already discussed, And the second section is about booth encoders. And then the third section is about approximate booth multipliers. In section 4, the evaluation and comparison with the state of art approximate multiplier is presented. Afterwards, in section 5, there is a case study of image transformation, and then in section 6, a conclusion is presented. Booth multipliers. Booth multiplier consists of booth encoding, partial product generator, partial product accumulation, and the final addition. In this section, accurate and existing approximate designs of booth encoders are presented. Booth multiplier take two signed inputs C and D of length m and gives an output of length 2m. So basically a radix 4 booth encoder. It uses three consecutive bits: the current bit, the previous bit, and the next bit. So they are encoded using three signals signs 1, 2, and the corresponding partial product is selected from the set, that is plus minus 2, plus minus c, or even plus minus 0. The sign signifies the negative partial product. One specifies the original partial product, and multiply by 2 indicates that the shifted partial product. So in the technical literature, the two approximate radix 4 encoders have already been proposed in R4 ABM1 and ABM1. The plus minus 2 x multiplicand is replaced by 0 and plus minus 1 respectively. Because of this approximation, not only that the encoder is simplified, however it reduces the logical complexity. After that, we discuss the radix 8 booth encoder. In the radix 8 encoder, the input D is grouped using overlapping 4 bits. Sign 1, 2 signals are used for the same objective as in radix 4, whereas the 3 signifies the need of old multiplicand and 4 specifies the 4C partial product. Higher radix encoding reduces the number of partial products significantly, so the partial product accumulation can be pursued by simple tree architectures. V. Leon and J. Zarevsky propose approximate high radix encoders where all the values are rounded off to the nearest power of 2. Such as in the case of 3, here we can see that it is rounded off to 2, and in the case of negative 3, we see it is rounded off to negative 2. Similar, and we can see that the error distance is just 1, as it is over here. Two approximate encoders R8 ABE are proposed and used to design HLR booth multipliers. A 16-bit multiplication is considered to explore the effectiveness of hybrid low radix encoding for the k-bit multipliers. HLR BM1 In HLR BM1, the 9 significant bits of the multiplier are treated with radix 8 approximate computation, whereas radix 4 encoding is used for the 7 most significant bits. The result is 7 partial products in total, out of which 3 are generated using approximate R8 ABE1, whereas the remaining 4 uh, are remaining for use radix 4 encoder. R8 ABE is designed with a concept to keep the absolute value of approximate product less than the exact counterpart. In R8 ABE1, plus minus 3 multiplicands are approximated to plus minus 2 multiplicand. Therefore, the proposed approximation generally results in the smaller than the exact value. Moreover, to keep error bounded, error difference is always kept as 1. HLR-BM2. HLR-BM2 is proposed using R8-ABE2, whereas R8-ABE2 is designed on the phenomenon that positive and negative errors in the logic complement each other. This allows further reducing the height of the partial product matrix. The 12 least significant bits of the multiplicand are encoded using approximate radix 8 encoder, whereas the remaining 4 bits are encoded using radix 4 encoder. R8-ABE2 is based on a simple yet efficient approximation approach. Therefore, as opposed to R8-ABE1, The input combinations are approximated to two different values instead of plus minus 1. Here we use plus minus 2. So 0101 and 1010 are approximated to plus minus 2 respectively, where 0110 and 1001 is approximated to plus minus 4 respectively. This method complements the error in the partial product reduction process and still maintains the error difference of 1 against the approximated values. Therefore, if two Booth multipliers are designed using R8ABE1 and R8ABE2 respectively, then the error in R8ABE2 based Booth multiplier will always be less than that of R8ABE1 based Booth multiplier. An approximate partial product generator. An approximate Booth encoder leads to the design of a simpler partial product generator, as we can see from the diagram. For both R8ABE1 and R8ABE2, this approximation simplifies the Booth encoder as 3 signal is no more needed. Moreover, in the partial product generation, plus minus 3 multiplicand is not required. This leads to a simple radix 8 partial product generator. Now partial product metric. In the approximate design, LSB are encoded using R8ABE encoders, whereas MSB are encoded using exact radix 4 encoder. Moreover, to further reduce the height of partial product tree, correction terms of the exact partial product is handled by ORing the recording sign factor with its respective vertical partial product length. The table shows the partial product reduction achieved by the proposed HLR-BM multiplier. HLR-BM1 has less number of partial product as compared to that of R4ABM1, and DRAD and RAD64 has the same similar number of partial product, but HLR BM2, as we already discussed, has least ED that is bounded to 1. So moreover, the use of R8ABE2 in HLR BM2, the complement error makes it a more favorable choice with respect to RAD64. So now we are going to discuss some terminologies, so it's better that we understand beforehand so it may not create any confusion afterwards. RED. RED is defined as the error distance over the absolute accurate result. NMED is the normalized mean error distance by the maximum output of the accurate design. MRED. MRED is the average of all possible REDs. And finally, PRED, which is the probability of obtaining a RED smaller than the specific percentage value. Here we have considered it to be 2%. Now, this table shows the hardware error matrices of proposed HLR-BM and existing approximate Booth multiplier. HLR BM multipliers achieve power saving of 18% to 31% over the exact radix multiplier. HLR BM1 has the least delay due to the reduced partial product tree compared to ABM1 and R8 ABM1 designs. Moreover, HLR BM1 has the power improvement of 7% to 14% with its comparative design having similar error matrices. HLR BM2 has lesser NMED than HLR BM1 because R8 ABE introduces both positive and negative errors. The errors complement each other and HLRM relies better error matrices. Now the figure shows the comparative performance of all approximate Booth multipliers by considering both energy and MRED. ABM1 has the least MRED among all the proposed design as plus minus 2 multiplicand values are replaced by plus minus 1 values. However, HLR BM1 having the comparable MRED to the previous best design has less energy. Similarly, HLR BM2 has improvement of 75% and 11% in MRED and energy respectively, with reference to the previous best energy optimized design, that was RAD 64. Now the next figure shows the energy gains of HLR BM2 with respect to its previous state of the art multipliers for large error values. 0.93, that is of RAD 1024, which is of RAD 1024, was selected as an error bound for all multipliers. HLR BM2 performs better for all designs except RAD 1024. And D-red generates less number of partial product. Therefore, for large values, the design show better energy error energy trade-off. Now the case study of image transformation. A 16-bit image was considered for the case study. In the paper, the pixel values are uniformly shifted from 0 to 65535. A predefined constant is multiplied by an input image to get a transformed image. Basically, by transformed image, we mean a brightened image here. So the peak signal to noise ratio and structural similarity index matrices have been used to assess the output image quality. As we can see that RAD256 has the worst quality, R4 ABM1 has the best quality because it has a smaller SSIM. The proposed approximate booth multipliers achieves a PSNR close to 50 decibels, but HLR BM2 had a better PSNR as compared to that of HLR BM1. So we can conclude the paper by saying that the use of hybrid approach, that is that using approximate R8 encoders and exact radix 4 encoders, has resulted in the reduction of partial product tree, and compared with the state of art approximate design, HLR BM multipliers actually show a better error and hardware characteristics, and also improvement in MRED and energy. Image transformation basically was used to evaluate the proposed multiplier. A PSNR greater than 50 decibels was achieved as mentioned. Therefore, it can also be used in error resilient application, and it can also find its application in digital signal processing. Now the relation to our course, we already discussed more booth multipliers in detail during our class, and we also discussed modified booth multipliers, so it relates to that. And then we discussed radix coding scheme. We discussed basically radix 2 and radix 4 coding scheme. However, the advanced state of radix 8 was covered in this. Most of the work was done from the paper. However, a few references were used as mentioned. The house is now. So thank you for listening to my presentation. Have a good day.